I can record and then I can enable that transcription stuff. Enable transcription. There we go. Okay. So we are talking about, sorry, let me go back here. The subject of calibration and validation. So method validation is proving that your method is linear and precise and accurate, has these various concepts involved. I don't know what you mean. I don't remember when it was made. I think I made it recently. Yeah. Yeah, I'm actually teaching right now, so sorry. Yeah. Sorry about that. I mentioned that HPLC is an excellent example of selectivity because in an ideal case, you can see your analyte and you can see the separately, you can see other potential interference, right? So that's a good example of that. And linearity you can get from this parameter R squared, which is, you know, I don't completely know how to interpret this number. You know, it's like the sum of the residual in X times the residual in Y squared over the sum of the squared residuals in X times the sum of the squared residuals in Y. I don't really understand that, but in any case, for a perfectly flat line where there's no actual correlation, where there's no slope, then R squared will be 0. And if there's a slope, R squared will be larger. But it depends a lot on the number of data points that you have. So, you know, R squared goes between 0 and 1, ideally. So, oops. I think a much better way is to examine the residual to your plot. And here, for example, this is the data from a fluorescence assay for quinine, where you have, sorry, I'm pointing to something you guys can't see here, where you have a fluorescence signal here versus quinine concentration. And you can see here that, you know, a line is not a bad fit to these data, right? This is not, it's not a terrible idea to have a linear fit here. But if you plot the residuals, you can see clear correlation between the residuals and the line. And the fact that the residuals are correlated here, that is that there is a shape to the residuals, is another way to say that, means that this model is not perfect. And you can see that at low quinine concentration, the model underestimates, and at intermediate concentration, it overestimates, and at high concentration, it underestimates again. Go back in your mind, rewind, and replace over with under, and then we're good. Sorry. So at low quinine concentration, the model overestimate, so the residual is negative. So so each d sub y is y sub I minus y. Right? Y sub I is the measurement, and y is the model value, right? And so anyway, so you can see that there's actually the data are actually curved, whereas the model is straight. So if we were to model this guy, you know, we can do this experiment. We get a correlation coefficient of 0.996, and that looks good. You know, that's a good sign. The correlation doesn't really catch the defect with the residuals plot, but it's still pretty good, right? So let's dive into this a little bit more deeply. And the intercept of this is 21% of the 3 mg standard. So that is a big red flag. So that means that the intercept of the line is positive, right? Here. And there's the 3 mg standard. And this is 20% of that 3 mg standard. So, oops, sorry. And that's greater than the 2% criterion that we put out for accepting this calibration. And so that the curvature in the line is revealed by the residual plot. Now, if you fit the calibration data to a quadratic function, and in this case, you get minus 2.25 x squared plus 171x plus 23.4, then the r squared value improves to 0.9998, right? Remember, the r squared doesn't care about the model. It's just x and y. And x predicted, or x, y, and y predicted, right? So and the intercept there in this case is still about 2% of the 3 mg standard. And so if we think about it, well, in this case, the fluorescence was zeroed using distilled water instead of sulfuric acid. And, you know, it's possible that the sulfate or the sulfuric acid could have given the fluorescent signal. You know, and if so, then the quadratic fit is appropriate. You know, we can play around with these concepts. But so how can you get to the question of accuracy here? And one way to do it is to use what's called a certified reference material. And a certified reference material is very carefully prepared, typically a very expensive material that you may acquire from NIST, the National Institute of Standards and Technologies. And the certified reference material is known to have exactly, say, 10 parts per million quinine in water, for example. And so a certified reference material is actually a material designed to help an analyst to measure a given analyte in a given matrix, right? So the matrix is everything in the sample other than the analyte, the solvent, and other components. And then the analyte is the thing you're measuring. And so, so if you have a certified reference material, you have an extremely good a good way to certify your method, right? Another way to do this is to compare two or more different analytical methods. So, for example, you could measure. One thing we're going to do in lab is we're going to measure toluene in acetone and ethyl acetate, right? We're going to measure that using UV-Vis. We're going to measure that using Raman, and we're going to measure that using FTIR. And to the extent that these three methods agree, we know that they are all accurate because they're quite different in the way they work. We could also use GCMS, and with any two or maybe three of those methods, then we can demonstrate accuracy of any one of the methods. So, and another way to do is to spike your sample, right? And that is to take a sample and measure it repeatedly to know how much your method tells you is there, and then spike it with a known amount of analyte. And and then what you can do is you can take the average of the unspiked and the average of the spiked and compare those and say, well, I know that I put in, say, 5 milligrams of the spike, and according to this assay, I put, it shows maybe 4.3 milligrams, and that would be an 86% spike recovery, and that would be that would be a red flag that your preparation method, the way that you prepare the standards, is losing some analyte. So we'll make a table of these approaches to ensure accuracy, these validation procedures, and I'll share that with you shortly. But spike recovery is an important one, and also you can do standard additions, right? And standard additions also, it's about the accuracy of a measurement. So in standard additions, you take every sample that you have to measure, you split, let's say, into 3 or 4 different 4 equal parts, say, or you could say, you could take your gallon of water or whatever and take 4 100 ml samples of it, and then you measure the first one without any modification. The second one you spike with, say, 1 part per million of copper. So, next one 2, 3, and 4 parts per million of copper, right? And then if when you're done, you see a linear increase in the copper concentration, then you can use that data to estimate the amount of copper that's in the original sample. So that's called the method of standard additions, and that helps to ensure the accuracy of your method. So
Professor?
That will go on our list, right?
Professor.
So let's say that we have, going back to this quinine case, a specification for determining that 3 parts per million quinine, it has a spike recovery of 100 plus minus 2%, right? So and let's say that we use the quadratic fit right? And that we talked about just a moment ago. And we have a spike of 1.5 parts per million, and that gave a signal of 194. And 4.5 parts per million gave a signal of 504.8, right? And this is a blank, so that we don't expect any fluorescence from the blank, right? And the question that we have on the table is, given those data, is this calibration method fit for purpose? Is this good enough, right? So so if we use the linear least squares equation, remember that we got 194 signal, and the intercept there was 72 and the slope was 92. That gives us 1.31 mgs per liter, right? And we actually put in 1.50, right? So the spike recovery is calculated as C for the spiked minus C for the unspiked over C added, right? This is the actual spike amount added in concentration units. This is what you measure for the sample, and this is what you measure for the blank, right? So we measured 1.31, the blank gave us 0, and we added 1.5, multiplied by 100, and that gives us 87% spike recovery. So this this method is not suitable using this linear calibration, right? And again, the 4.67 concentration, that's 103.8% spike recovery. So that's above the maximum. This is way below, that's above the maximum. So so this method lacks the necessary accuracy, right? So let's go ahead and do an example here. If the blank is spiked at 3 and gave a signal of 354.4, what is the predicted quinine concentration and the percent recovery? So what we want to do there is, here, we can do that in the on my webcam here. Let's see if I get this guy. Oops. I'm gonna turn my camera on. Hold on. So hold on just a sec. I'll get my share back. Put my microphone closer to my mouth here. Sorry about that. And I'm going to get back to the, oops. So this is the problem that we worked on in class, or just a second ago. And so this was not acceptable. Right. And now what we can look at is this new case where we have 3.00 ppm spike, and the signal was 354.4, right? And what we need to assess this is we need the equation, right? And the equation is y. This is y, the signal. And the signal is equal to 92.4 times x plus 72.9, right? That's the linear equation for this guy. And so let's just see. Now what we want to do is we want to solve this for x, right? So we have signal minus 72.9 divided by 92.4 equals x, right? And we're going to put in the signal that we got with our 3 ppm spike here. And so we're going to put in 354.4 minus 72.9 divided by 92.4, and that will equal 281.5 divided by 92.4, which will equal 3.05 ppm, right? And so now for our spike recovery, that guy there, that guy there is equal to C spiked minus C unspiked divided by C added. And this is the nominal value. And these guys are measured. And that will equal 3.05 over 3.00, and then this is times 100%, right? And this will equal 3 minus 3 divide 100 times. Oops. So 3.05 enter, 3 divide 100 times. This is 101.6, which is also unacceptable based on our criteria, right? So this is one example of how to compute a spike recovery, and in this case, compare it to an imposed criterion for acceptability, right? And so this is what we just did up here. So, all righty. So,
Professor?
yes.
Wasn't the standard from 98% to 102%?
Oh, right. Sorry. Yeah, you're right. So this was acceptable. Sorry. Sorry. Oops. It was acceptable. Oops. Oh, okay. So let me see here. Let's go back to this guy. Oh wait, I need to bring it back in this way, right? I need to go. There we go. No, that's not what I'm doing. Jake, I'm all flustered today. What's wrong? Let's see. New share. Let me see. Probably you guys, are you seeing a screen that says types, and you can see my mouse, it says types of precision?
Yes, we can see the types of precision.
Can you, is it in a like a window with all kinds of button bars and stuff around it, or is it full
Yeah,
screen? Okay. All right, I got it on the wrong one here. Let's see here. Ah, here we go. There we go. That's better. Oh gosh, I would just be such a disaster as a news anchor or something. I don't know why. I'm just like, I'm trying to get the stuff right and everything's going all to hell. Oh well. All right. So there's a variety of types of precision that we care about. Instrument precision, obviously, that's one of them. Intra-assay precision is just different specimens measured by the same person in the same day with the same equipment, right? So, or it could be different specimens of the same material, right? So you measure it in the morning, you measure it in the afternoon. If you get the same answer, that's good intra-assay. So intra meaning inside the same assay. The assay meaning the analyst and the instrument and things like that. So intermediate precision here is different people, different instruments, different days, right? And that's a higher standard, obviously, for accuracy. And then interlaboratory precisions is where you take the same sample and analyze it by different people in different laboratories, right? So that's like the highest standard for precision, right? So now it turns out that these things are quite difficult to assess. And there's a thing called the Horowitz Trumpet here. And it basically says that the lower the concentration is, the more difficult this intra-laboratory assay is. For if you think about just like things in food, right? Say for major nutrients, they may be there. This is like proteins, fats, carbohydrates, and stuff. They may be up to like 10% of given food stuff, right? And in that case, the interlaboratory precision might be, between, plus or minus 5%, right? If you get down to minor nutrients, things like that, where the detection limits go down to 10 to the minus 6, 1 part per million, then the interlaboratory precision goes down and the standard deviation goes up to plus or minus 15%, right? And then nobody really knows for lower values, like aflatoxins here, which are they're proteins found in peanuts, and they're for, I think, green peanuts or something. They're just really super toxic sometimes, but they're really trace, So if they're present at 10 to the minus 9 concentration, it's hard to say what the interlaboratory precision on that would be. It could be plus minus 25%. It could be more than 100%, right? Which is weird because it implies that one laboratory might actually get a negative concentration. But that's really the reality, even though an analyst would never publish or present a negative concentration. The implication is of this dramatically increasing standard deviation between laboratories is that as concentrations go to zero, the reliability of analysis goes way down. So this is a cautionary tale. It's not meant to be a general criticism of all low concentration results, but more like something that you want to be careful with, right? Especially when you're analyzing low concentrations. And so you know, they call this the Thomson plateau, whatever. I don't believe this, you know. So in any case, there's nothing quantitative we need to do with this. So range, there's the linear range, there's the dynamic range, which is, and there's a linear dynamic range, right? Which is the intersection of those two concepts. And it's basically just talking about the calibration curve, the range over which it continues to change, and then the range over which it's linear. And then a robust calibration will be one that's not sensitive to small deliberate changes by operating parameters. So an example here might be a pH measurement, right? And if your pH meter is sensitive to the stirring that you're applying to this sample, then you would say, oh, this meter is not robust, right? Or the temperature or the ionic strength is a very common problem for pH measurements. So these are just ways to talk about a method, you know, what its range is, how robust it is, things like that. So coming back to the idea of fitness for purpose, here's, oops, didn't we already do this? Geesh, we already did this. Huh. I guess we must have gone forward, or maybe this is repeated there. Any case, now there's a concept called limit of detection, right? And it's a simple one to ask questions about, so that type of question can come up. It does come up in the homework, and let's talk about it briefly here. The detection limit is the lowest concentration, or that produces a signal that's significantly different than blank, right? And so what one can do is one can take a blank and develop a hypothetical distribution around that blank, right? The probability distribution for the blank, right? And this might be some concentration, or this might be some signal level, could be any arbitrary number, right? Let's say it's 10 and it has a standard deviation of 1, right? But because it has a standard deviation of 1, any particular blank that you may put in might give a 9 or a 10 or a 9.9 or 10.1 or something like that, right? So to be conservative, we tend not to report concentrations, the signals for which are less than 3 standard deviations above the blank. Does that make sense? So for example, Logan, if I were to sort of throw something out and challenge you, and I were to say, oh my gosh, Logan, your this cancer marker is, we measured it and it's 1 milligram per liter of blood in your blood, right? And you might be super smart and say, well, what standard, what standard deviation does that method that you measured this with return? And if I said, well, the standard deviation is 2, the standard deviation in concentration units is 2, would you be concerned?
I don't think I really understand the question.
Okay, so let's say that you go in and you have a blood test, right? And they go through, and this is one thing that I get every year, and it's for colon cancer, right? And they measure this, they measure blood, right? They measure for blood. And every time they measure, they get a signal corresponding to the amount of blood that they found, right? And the blank, in this case, gives a signal, right? And the signal could be 100, let's say, right? And let's say that my sample came back and the signal was 103, right? Or your signal came back and your signal was 103. So the question is, should you be concerned?
And then with the standard deviation of like 2, would that still apply? And then that's like a 3 above it. So then I would say, yeah.
Right, exactly. So if the standard deviation on that measurement were 2, and I say you got 103, right? Then might be cause for concern, right? How about if the standard deviation were 10?
Then probably not.
Yeah, that's right, because it's extremely unlikely for any measurement to be outside of the, the 100 plus or minus 15 range, right? And so all blanks are going to be producing, a value of 100 plus or minus at least 2 standard deviations, right? 1 standard deviation would be about 70% of the values, right? So as chemists, we sort of take this to heart and we say, well, I'm not going to even say we detected anything until the signal is above blank by 3 standard deviations, right? So if it's a blank, it's the likelihood of, if it's actually what's going in is actually a blank, the likelihood of seeing this would be 1% or less, right? So in that case, we're going to report the concentration that we measure, right? But if it's less than 3 standard deviations from the blank, we're going to say, well, we did not detect anything, right? We didn't detect anything above, within, outside of 3 sigma from the blank. Jeffrey, does that make sense to you? Do you think Jeffrey's here? Or is he stealthily leaving his little icon there and playing World of Warcraft or okay. John, are you here?
Yeah, I'm here.
I love it.
It makes sense.
Makes sense?
I think so.
Yeah. Okay. All right. So so if I say a method, let's say the method, just for weird reasons, has a slope of 1. The calibration slope is 1. You got 1 part per million, you get 1 signal unit, 2 part per million, 2 signal units, right? Etc. And I say this method has a standard deviation of 3, right? 3 signal units, 3 parts per million, right? That's just sort of speaking the same language there, right? What is the minimum detectable signal in that case?
Will be 4.
So 4 would be greater than 1 standard deviation, right?
You said like if it's three standard deviations, right?
Right. And did I say the standard deviation was 1 or?
Oh, you said it was 3, so it's 3 times
Yeah.
3.
Right. Yeah.
Right.
So standard
Sorry,
deviation,
That
right?
was 1.
Yeah. So the detection limit in this case is what?
Nine.
Right. Exactly. Yep. Let's see here. I gotta find this chat. Yeah. So it's 9 actually. So it's 3 sigma. Sigma is 3. 3 times 3 is 9. Good. Okay. Cool. So anyhow, that's how you do that. And so one thing to do here is you know how you get the uncertainty in the intercept, right, of a calibration curve? That is a measure of the 3s or of s for the sample, right? So you can take that uncertainty in the intercept and divide it by m to get the sample concentration, and then multiply that by 3 to get the minimum minimum detectable concentration, right? So S is also the uncertainty in the blank signal. And when you do linest, you get an uncertainty in the blank. So 3 times the uncertainty in the blank divided by the slope is equal to the detection limit, or the minimum detectable concentration. Okay, moving forward. For quantifying a signal, so if you get something right at 3, then you say, well, it's probably less than, you know, we believe we've detected something, but we don't know how much, right? This is pretty conservative, right? And until you get up to 10 standard deviations, you generally don't, you're not supposed to quote the actual value. And it's a funny thing, right? Because I've been sort of preaching this stupid dogma for many years, right? And I just inherited it because I never had this class. I just had to teach the stupid thing. So I dove in feet first, right? But we were doing, I think it was atomic absorption, and this student did the calibration curve, and he got enough fluctuation in the signal, enough sigma b, enough standard deviation in the intercept, that although his signal was like right sort of like in the lower half of his calibration curve, it was not above the detection limit. And so that's what he reported. And I was like getting all ready to write it down. And like, he's like, you know, it's not detectable. It's like, darn it, he's right, you know? So anyhow, you'll see that. You'll see that'll come up for you. Hopefully not, actually. So okay. So let's not do this now. You can maybe do this one at home or something. It's kind of detailed, and I'll probably screw it up anyway. So so here's an example of a reporting limit here, right? 5 to 10 times the detection limit. Yeah. All right. So standard additions, right? Let's talk a little bit about standard additions. Standard addition the idea of standard additions is to improve the accuracy of a calibration, right? And the idea is that if you have, let's say you want to measure something in your fish tank, right? You want to measure amines, right? That's a real common like toxin for fish, is the amount of amines in the fish tank. And amines could be ammonia, or it could be, you know, any one of a number of organic amines, things like this, you know, methylamine, ethylamine, things like that. And you can do assays for amines in a variety of ways, right? There's ways using phenol and other things. But if you measure your aquarium sample, but then you calibrate the method using pure water, right? Pure amines in pure water, how can you know that your method is accurate, right? How can you know that your method responds in the same way to the amines in the aquarium water as it does to the amines in the pure water, right? So, for example, you could do this, right? And let's say that the amines produce a purple color, right? And you measure this purple color that develops in pure water, right? And then you take some aquarium water, right? And you measure it, and it's slightly purple, right? You say, hey, you know what? What if I took the same amount of, I took another bit of water, then I intentionally added some ammonia to this, right? Then I do the whole thing, and I want to see how much this extra ammonia adds to that signal, right? Is that going to be the same as if I added that amount to pure water? And what do you think will happen there? Who can, Cassie, can you volunteer something there? I mean, I'm talking about aquariums
Oh,
here. So yeah.
yeah. I mean,
So
it's-
yeah, uh-huh.
it kind of makes sense. I'm just not sure if like my
yeah. So if you measure your amine in pure water,
Mhm,
and it gives this beautiful slope, right?
mhm.
But then you try to simulate the aquarium water, right?
Okay,
Will you have exactly the same slope in the aquarium water?
probably not.
Right. It doesn't seem likely, right? It
Mhm.
might happen or it might not, right? It's
Yeah.
very reasonable to expect there to be some difference, right? So what you do in that case is standard additions, right? And now standard additions are not perfect, right? Because it's hard to find the analyte in just the exact same way as it is in the aquarium water, you know, but it's way better than calibrating in one matrix and measuring in another matrix. Does that make sense?
Yeah, that makes sense now.
Cool. So uh so uh so this method does require a linear response. So it only works for linear calibrations, right? And uh, it's appropriate when the sample composition is complex, it's unknown, or it affects the analyte signal, right? So there's some interference there, right? So for example, here, uh, you know, you can measure, you know, detector signal in a matrix, you know, by ESI and by APCI. These are different mass spec methods, you know. And you know, you can show that, like, if you add the matrix in here and plot the detector signal with the matrix versus the detector signal without the matrix, you know, in some cases the matrix enhances the signal, and in some cases the matrix depresses the signal, you know. So it can go either way, right? And there's a way to analyze it. This is a very general way. It's also a little complicated, and so this is why it's written out here in this kind of big old, like, bold way, right? And I'd kind of like to come back to this, right? Because I'd like you to analyze this curve. Actually, so let's think about this one here, right? I think this is a better place to start. if you have, let's say this is your aquarium water, and you take 5 equal aliquots, right? 5 mils, 5 mils, 5 mils. So you take out 25 mils of aquarium water and you split it 5 ways here. Well, yeah. So you get 5 in each, right? Then you add 0 standard to this, then 5, 10, 15, and 20 mil of a standard amine, right? So this is just aquarium water. It has probably some amine in it, right? The amine is from the fish pee. Did you know that fish pee in there, right in the water they swim in? Is that not shocking? Okay, I'll shut up now. So you get only the fish pee with some amine, more, right? And the signal from that increases linearly, right? And then the intercept from that is down here on this axis, right? And that intercept is minus the x-intercept, right? And this intercept here tells us how much concentration was originally in this sample, right? So this is super dependent on you having a good blank correction for your signals too, right? Because there can be 0 offset here. So you're relying on the fact that at 0 concentration, this signal goes to 0. But if that's the case, then you can go down to this point in the axis here, and you can read off the concentration that's in the original diluted sample here, right? It's almost like it's just shifted over by this many concentration units here, right? Somebody help me out here because I am losing faith. I'm dying. Somebody help me.
Help
Help
out.
me. Help me, please. Ah, how? Okay, how to help me? Tell me that this makes perfect sense.
It sounds like we made 5 samples and then we
Yes.
made a slope. And then
Yep.
we just
Right. How do we get the slope?
by analyzing the
Each 5 sample, we know how much analyte we add.
yeah.
We know the signal we get, right?
Yeah.
Add some analyte, add some signal, add some analyte, right? Then, and
That's like
then
just given to us.
Yeah,
yes,
the
computer will
signal
spit that
over
out.
the amount.
yeah. What Snigda?
Never mind.
Oh, come on.
Never mind.
Ah. Okay. So, Carla, do you have anything to contribute?
No, I'm just following along.
Okay. Does so far make sense?
Yeah.
Okay, cool. The rest is really nuts and bolts, right? Is anybody kind of lost right now? Show of hands. If you're a little bit lost.
When
Yeah.
we do this, like will
Yeah.
the computer program we're using, like will it give us B?
Yeah.
Okay.
Yeah. Yeah. So actually like what you get from the computer is sorry, I gotta come back, is mx plus b, right? Y is equal to mx plus b, right? And if you plug a 0 in for Y, then B is equal to minus, and that, wait,
X is equal to negative B over M.
right, sorry. Yeah, exactly. So I didn't see that, but like, what? Yeah, exactly. So, so yeah, so you can find, and there are many programs that will return that are like kind of made to handle standard editions. And it's interestingly like the not for HPLC, for example. HPLC does not give a crud about the matrix, right? In HPLC, you take a little bit of your sample and you inject it into a flowing stream, right? And then what happens is all the analytes or all the components in that mixture begin to separate. And they separate in a stream of flowing mobile phase, right? And then by the time they reach the detector, they are all in the same matrix. Does that make sense? Miranda. I'm just picking randomly on little black squares on my computer. Okay, Katie. Uh-oh. Everybody's getting snacks. Katie's here. Yay. So do you know how HPLC works? Yeah,
Kind of.
kinda, yeah. So you inject your sample, you can inject like 5 microliters, a little like a quarter of a drop or so, into this stream of flowing, say, water or acetonitrile or some solvent, right? And then that goes through a column, and then the column slows different molecules down by a different amount, right?
Okay, yeah.
So by the time these molecules get to the detector, their matrix, that is all the other stuff around them, it's all the same. It's like it's all, let's say if you were running in 30% methanol and water, then they get to the detector and molecule A is in 30% methanol water and it goes by, and then molecule B comes up and it's in 30% methanol water, right?
Okay.
Okay, so so for that reason, well, let me just ask you then, is standard additions a good method to use with HPLC?
I think so.
No.
I don't know.
Excellent, excellent. So the answer is no, because standard additions is about everything else in the mixture affecting the signal that the instrument gives you, right? It's about matrix effects.
Okay, yeah, that makes sense then.
Yeah, cool, good. All right,
Professor,
so yes,
why
yes.
is it more precise to, like, when doing standard additions, to add by mass and not volume?
Oh, that's kind of an irritating thing to add right there, because the only reason that it would be more precise is because at a higher concentration, things tend to be more precise, right? If I take, if I'm measuring vitamin C in fruit juice, right, and I can measure it in right in the orange juice, right? I might get, 50 milligrams per 100 mils, right? Then if I take that and I dilute it by 100, then I'd get 0.5 milligrams per 100 mils. And that might be real close to the detection limit. And that's not as precise. So I was actually asking myself that I got to go through this and I got to weed out those stupid kind of things that are in there. It's not a good point to make there.
Got it.
Thank you. Okay, so this is Chem 55 stuff, right? And I sucked at teaching Chem 55, but I'm good at teaching Chem 155. So I'm going to leave that there, right? And we'll do a couple of examples, and I pretty much promise that I won't do this on an exam. On standard additions questions on an exam. I might ask why you would do standard additions, or if you would do standard additions with an MIP or an HPLC, right? MIP is microwave induced plasma. And that's something where you might do standard additions. But HPLC is not suitable for standard additions because all you're going to do is dilute your sample. Okay. So those are the more type of questions that I'll ask for this class. Okay. So internal standards. Now, an internal standard is something that you add to your sample and your blank and your standards. Or maybe not to your blank, but at least to your sample and your standards, right? And what the bleep is an internal standard? Okay, an internal standard relies on a detector that can separate things. So, for example, an HPLC. An HPLC, let me share here. We'll share camera. Internal standards. Their job is to control for random fluctuations in the instrument response. Does that make sense? So, for example, in an HPLC, you've got a syringe that injects a certain amount. Boom, it injects, let's say, 5 microliters, right? Does that make sense? And what if there's some jitter in this and it goes 4.5, 5.1, 5.0, 5.3, 4.9, 4.8, right? There's a lot of jitter in that value. Then the peaks that you get for this are going to be large, a little bit smaller, little bit larger, a little bit larger, that kind of thing, right? There'll be a variation in the peak amplitude right? Depending on the injection volume, right? So what can you do to correct for that, right? I'm exaggerating the effect, right? But who knows? So what you can do is that you can add another component that has no interferent. Okay, just focus on adding another component right now, right? So you can say, well, we got 4.5, 5.1, you know, whatever. And then this goes to a peak height of, you know, 100. And then this goes to a peak height of, I'm sorry, this goes to peak height of 90. This goes to peak height of 110, etc. But the concentration is, you know, 10.0, 10.0 parts per million in each case, right? But the injection volume fluctuates, so the signal fluctuates, right? Are you following me, Snigdha? Yes.
Kind of. I just need to take it in.
Okay, cool. So now what we do is we add another chemical. Let's say this is caffeine, right? We could add some benzoic acid, which has its own peak, and we'd say 10.0, 10.0, 10.0, and this guy gives, you know, sorry, 10.0. This guy gives, let's say this guy gives 40, 45, and what would it give here? Well, here it would give 55, right? And 90 over 45 is 2.0. And 110 over 55 is 2.0. 2.00 exactly, right? So the presence of the internal standard here, this guy is the internal standard, which can be measured independently right? It allows us to correct for instrument fluctuations. Right? Does that make sense?
Professor,
Yes.
how do we know that the signal for the benzoic acid would be 45 and 55?
Okay, so I know. Thank you, Logan. No, Emily. Good. So I'll answer this. Then I've gotta stop. Right, but so sorry. This would be. So I know that if it's 90 here, it's half it there, right? And if it's 110 there, it's half of it there. Right. So I think probably should have been 5.5 here. You know, but there's this relationship, right? And so the thing about it is that for this is the part that we don't know about. We don't know how the injection volume is varying, right? This is hidden from us. I mean, we just don't bloody know, right? Because it's a a malfunction in the instrument, right? And it doesn't tell us, oh, I under injected or I over injected. It says, I tried my best, right? I don't know how much went in, right? You know, so uh so so the internal standard signal, because its concentration is constant in all the samples and everything, right?
Mhm.
We know that if its amplitude varies, then the instrument is at fault for that, right? Because we know the sample is not.
Right.
So if the instrument overestimates the internal standard, it also overestimates the analyte. If it
Okay.
underestimates, yeah, and so you can correct it by dividing out by the internal standard concentration. Yay!
Right.
I taught somebody something. I can't believe it.
I
Yay.
still need to review this.
Okay, good. And it's, I wish you the very best of luck. And I think I'm probably gonna have to add some time. I think I'm gonna make the friggin' chapter 5 homework due next week or something. Because we're going slow, but it's just slow going. It's just the way it is. So today's Wednesday, right? So I have to do that. And I'll just change it. I'll just, hopefully you'll get 2 notifications that chapter 5 is going to be due let's say next Wednesday night. Because I'm in big trouble here because I'm just always overestimating the rate at which we can teach this stuff. But expect another change there. Okay, everybody. Thank you so much. Thanks for listening. And I have to drop the mic here. Bye-bye.
Thank you.
Oh, and Monday is also online. Thank you, Sharon. Monday's online.
Thank you.
Okay, bye-bye.
Professor, I had a quick question.
Yeah.
I may have misplaced my tablet pencil in lab.
Oh, it's yours.
Oh, you found it?
Yes, we found it in the lab. It's a
Okay.
big old white thing with a USB charger in the end, right?
Oh no, mine was gray.
Well, whatever, white, gray, but it's like, it's kind of flattish, right?
Yeah.
Yeah, that's the one. Yeah, we got it for you.
Are you on campus right now? Because I can make it to Duncan Hall and pick it
Oh
up.
no, I'm running from here, running.
Okay.
Yeah,
Can I
so
come up tomorrow morning then.
yeah, come tomorrow morning. I'll be in lab.
Okay, sounds good. I'll be there. Thank you.
Okay, all right. See you soon.